The theory of prehistoric cosmic detonation is generally acknowledged by most researchers as the essential clarification for the origins of the universe, enveloping the production of stars, planets, and all life, including us. Notwithstanding its fairly unconventional name, the term Big Bang appropriately captures the immensity of the occasion. At first, the universe was a thick assortment of particles pressed into a space smaller than a pinhead. From this minute point, an enormous blast of matter happened, known as the Big Bang. This concisely sums up the interaction that unfolded over billions of years. However, regardless of the persevering fame of the theory of how things came to be, progressions in scientific knowledge have progressively challenged its predictions. When NASA sent off the James Webb Space Telescope, the largest and most advanced space observatory to date, scientists speculated that its observations would reinforce the theory of prehistoric cosmic detonation. Unfortunately, after only 1 year in space, the telescope has dumbfounded researchers with its momentous capabilities, giving extraordinary looks into the universe's past. The James Webb Telescope's discoveries have revealed systems so old that they might actually reshape how we interpret the universe's origins. This unexpected disclosure has sparked intense interest among researchers and fans alike. One such noteworthy disclosure came when stargazer Rohan Naidu, analyzing early pictures from the James Webb Telescope, accidentally found a system that surprised everyone. This universe, named Glass Z13, seemed mysteriously gigantic and traced back to only a short time after the Big Bang, making it older than any previously noticed world. Naidu's energy was tangible as he imparted the revelation to partners on the planet, describing it as beyond anything astronomers could ever imagine. The James Webb Telescope, positioned far from natural impedance and furnished with state-of-the-art innovation, was intended to dive into the universe's earliest age, known as grandiose sunrise. This period, covered in mystery, denotes the formation of the universe's most memorable stars and worlds. By examining systems from this period, researchers hope to refine how they interpret major cosmic cycles like the impact of matter and dark energy. Initial assumptions for the James Webb Telescope's discoveries were humble, expecting a couple of weeks far-off universes. However, the reality surpassed all projections. The telescope's pictures revealed systems of amazing development, challenging existing models and provoking a whirlwind of examination. As researchers continue to dissect the James Webb Telescope's data, the ramifications of these revelations could be significant, introducing a new era of cosmological comprehension. The surprising disclosures from this noteworthy observatory offer a tempting look into the universe's past, driving humanity's journey to unravel the secrets of existence. As early systems materialized, scholars and spectators ended up in a scramble to make sense of them. Might this gathering of oddly enormous and bright early worlds ever be fanciful, perhaps due to flaws in the examination of the telescope's initial perceptions? Or, if authentic, might they ever somehow be accommodated with standard cosmological models? Quite possibly, were they the main means that the universe is stranger and more complex than our boldest speculations had assumed? In question isn't anything less than how we might interpret how the precise universe we know arose out of early-stage confusion. The early disclosures from the James Webb Space Telescope can possibly revise the initial parts of grandiose history. These sections concern far-off ages in distant systems as well as our own presence here in the natural smooth manner. As Mark McCarran, a senior counsel for science and investigation at the European Space Office involved with JWST, commented, "You build these machines not to affirm the worldview but to break it. You just don't have the foggiest idea how it will break." In a way, JWST perceptions of early universes have been billions of years truly taking shape. Nonetheless, more unobtrusively, they trace back to the Space Telescope Science Foundation in 1985. Around then, the Hubble Space Telescope was as yet 5 years from send-off. However, the establishment's then chief, Ricardo Jan, requested that his group begin contemplating what might come after Hubble. A lot further away, regardless of initial fights about zeroing in on Hubble, Jan was tenacious, predicting the extensive development process. Guy Linger, then deputy overseer of SD Sky, alongside a little group, began drafting thoughts for what in the end turned into the Cutting-Edge Space Telescope, later renamed JWST. They perceived that while Hubble would be groundbreaking, its capabilities would be restricted by its perceptions in noticeable light. The NGST, then again, would see in the infrared range, permitting it to enter further into the universe. The need for JWST turned out to be much more obvious in December 1995 when cosmologists directed the Hubble Deep Field Perception. In spite of assumptions for finding a couple of faint cosmic systems, the subsequent picture uncovered a huge number of worlds extending back more than 12 billion years into the universe set of experiences. After over 20 years of improvement and at an expense of around $1 billion, JWST at long last sent off on Christmas Day 2021. The telescope went through thorough testing prior to arriving at its profound space objective a month after the fact. By July 2022, it was prepared to begin its hotly anticipated first year of science perceptions, known as Cycle 1. Some portion of JWST's initial mission was given to high-impact programs, including the Astronomical Evolution Early Release Science Survey and the GRISM Lens Amplified Overview from Space, both aimed at revealing insight into the secrets of the early universe. As stargazers openly gave endless hours to scanning separate patches of the sky looking for early universe cosmic systems, they at first expected modest discoveries similar to a more detailed variant of the Hubble Deep Field. In any case, they were in for a shock. Stephen Finkelstein from the College of Texas at Austin, leading the SE project, makes sense of that very far-off systems were supposed to arise solely after numerous information cycles from different projects. However, to cosmologists' wonder, these universes showed up very quickly. Previously, the record for the most far-off known system had a place with GN-Z11, seen in 2015 with a redshift of 11. Redshift measures the expanding of light because of the universe's expansion, with a higher worth demonstrating greater distance. Yet, from the very beginning of glass perceptions, two separate groups, including one drove by Rohan Natu, independently recognized glass Z13 with a redshift of 13, driving the enormous timetable back significantly further. In their scramble for quick results, specialists depended on worked-on techniques for redshift assessment based on brilliance estimations, as opposed to additional time series direct estimations. In spite of their effortlessness, these evaluations uncovered worlds suddenly brilliant and enormous, some previously flaunting a heavenly mass equaling 1 billion suns, much like our own. The energy didn't stop there. In the subsequent days, numerous universe competitors from soothsayers and glass arose, some with redshift gauges as high as 20, indicating they existed only a short time after the enormous detonation. These worlds showed circle-like designs not expected in such early astronomical ages. Furthermore, another group found proof of smooth waste systems at a redshift of 10, under 500 million years after the enormous detonation. Such a fast rise of sizable universes challenges the expectations of the standard cosmological model, lambda cold dark matter. To grasp this oddity, a brief return to early universe elements is fundamental. In the initial minutes after the enormous detonation, the universe was a hot, thick soup of early-stage particles. Over the long haul, as the universe extended and cooled, helium and other light components formed, leading to the presence of the principal iotas around 400,000 years later. Approximately 100 million years after the enormous detonation, conditions became conducive for the development of the principal stars, made essentially out of hydrogen and helium. These early stars, bigger and more splendid than current stars, amassed into proto-worlds, directed by the gravitational draw of dark matter. However, JWST's revelation challenges this model as it uncovers brilliant, sizable cosmic systems far sooner than anticipated. Stacy McDaw from Case Western Reserve College noticed the startling shortfall of numerous smaller protogalactic parts, suggesting that some noticed systems might be closer than assumed, hidden by dust, seeming dimmer and more far off. The discovery of the early worlds brings up significant issues about the universe's early stages, highlighting the need for continued investigation and revision of our cosmological models. Follow-up observations of glass Z13 in August 2022 by the Atacama Large Millimeter Array in Chile cast uncertainty on the initial findings. Despite the use of brilliance-based estimations, ALMA didn't detect significant amounts of dust associated with glass Z13. As Peter Tom B. from Goya College, who led the observations, said, this suggests that low redshift intruders can be excluded, but ALMA attempted to identify the universe by any means. This highlights the challenge of confirming observations made using JWST's high capabilities. Rohan Natu, one of the specialists involved, pointed out the incongruity of the situation, stating, "The good news is there's nothing identified," he said. "The bad news is there's nothing identified." With only JWST capable of following up on its own observations, the most frightening explanation could be that the standard lambda-CDM cosmological model requires updating. Michael Boylan-Colchin, a cosmologist, expressed the size of this potential shift in understanding, stating, "These outcomes are extremely astonishing and difficult to get in our standard model of cosmology. It would be a genuine revolution to comprehend." One controversial proposition is modified Newtonian dynamics, MOND, which challenges the existence of dark matter. JWST observations could lend backing to MOND, proposed by Mark McGaugh. However, not all cosmologists are persuaded of MOND's validity. Another possible explanation is that early universe worlds might have almost no dust, causing them to appear more splendid and affecting mass computations. This scenario could also explain ALMA's difficulty in identifying glass Z13. Charlotte Brinkley and her associates proposed that JWST could be observing the most brilliant young systems in the early universe, which could suggest unique star formation conditions during that age. David Spergel supports this idea, suggesting that high-mass star formation could have been more efficient due to higher gas tensions and temperatures, potentially influenced by early magnetic fields. The quick dispersal of scientific papers from JWST's initial observations reflects a shift toward real-time peer review via platforms like AR14 and social media. While this speeds up the dissemination of findings, there are concerns about rushing to conclusions before thorough peer review. Despite calibration issues and potential recalibrations affecting some results, it's unlikely that all high-redshift cosmic systems observed by JWST will be nullified. The sheer number of these worlds suggests that the early universe might be different from what was previously anticipated. Stephen Finkelstein expressed confidence in the validity of the discoveries, stating that the chances of cosmologists being altogether wrong are small. Presently, stargazers are hurrying to conduct subsequent observations with JWST. Nancy Levinson is currently evaluating around 12 proposals from various groups seeking additional JWST observation time, primarily to examine high-redshift cosmic system candidates. Given the excitement and significance of these early discoveries, confirming them is vital. Troy Hull, who submitted one of the proposals, underscored the importance of confirming these findings. Different projects, like Cosmos Webb led by Caitlin Casey, aim to expand the known population of early systems by observing a wider area of the sky for many hours. They anticipate identifying thousands of systems. Additionally, extra undertakings will look for proof of the first proto-universes, possibly using the explosive deaths of supersized first stars and radiant supernovae as markers for their existence. Some evaluations suggest that JWST could observe cosmic systems to the extent of a redshift of 26, only 120 million years after the enormous detonation. Confirming even a small number of these high redshift candidates would be a remarkable accomplishment, according to Natu, showing that cosmologists are not being misled by their observations. JWST has introduced a new era of science, and despite the uncertainties, the rapid communication of new data has invigorated astronomers. Troy Hull expressed excitement about the associated academic community's enthusiasm. Now the question arises as to whether it's time to reconsider how we interpret the very beginning. Artie pondered the significant ramifications of delving into the unknown, concluding the information for now. Remember to show your support by liking, subscribing, and hitting the bell for future episodes. Also, be sure to share your thoughts on today's content. Your support inspires us to keep delivering quality content and striving for progress. Thanks for watching, and we'll see you next time. In conclusion, the James Webb Space Telescope, JWST, has ushered in a new era of exploration and discovery, challenging our understanding of the universe's origins and evolution. Its unprecedented observations of galaxies formed shortly after the Big Bang have sparked excitement and debate among scientists, pushing the boundaries of cosmological knowledge. The telescope's ability to peer deeper into space and time than ever before has unveiled cosmic phenomena that defy conventional models, prompting a re-evaluation of existing theories and the formulation of new ones. From ancient galaxies to the mysteries of dark matter and early star formation, JWST's findings have profound implications for our understanding of cosmic history. Looking forward, JWST promises to continue unraveling the universe's complexities, offering glimpses into epochs previously beyond our reach. Its discoveries not only advance scientific inquiry but also inspire wonder and curiosity about the universe's vastness and our place within it. As JWST embarks on its mission to further explore the cosmos, scientists eagerly anticipate what new revelations lie ahead. With each observation, we move closer to unraveling the fundamental questions of existence and gaining a deeper appreciation of the tapestry that surrounds us. In essence, the James Webb Space Telescope stands as a testament to human curiosity and ingenuity, driving us toward a deeper understanding of our cosmic origins and our place in the universe's grand narrative.